When you think of a tsunami, you imagine an earthquake, right? A catastrophic wall of water triggered by the ocean floor shifting. But what if I told you that the last great worldwide ocean wave event was triggered by something else entirely? Something invisible, traveling through the air at the speed of sound. This is the story of the Hunga Tonga Hunga Ha'apai eruption of January 15th, 2022. It wasn't just a blast of ash and steam. It was the largest atmospheric explosion recorded on Earth in over a century. It created a pressure wave so powerful, so immense, that it generated an ocean wave, a planetary meteotsunami, that didn't just cross the Pacific. It circled the entire world. Not once, not twice, but 3 times. Welcome to the channel. Today we're diving into the extraordinary science behind an event that rewritten the book on ocean dynamics. The Tongan eruption was visually stunning, but its true scientific marvel lies in the atmospheric wave it produced. Scientists call the primary atmospheric disturbance a lamb wave. Think of it as an immense pulse of pressure, a sound wave trapped near the surface, traveling at the blistering speed of roughly 700 miles per hour, or 310 meters per second. This pressure wave didn't just disappear. It became the driver of the planetary ocean wave. But how does an air pressure change in the sky move the entire ocean? The answer lies in the little-known phenomenon, the meteotsunami. A meteotsunami, or meteorological tsunami, is an ocean wave generated by atmospheric disturbances. It's not a seismic event. Ordinarily, a small pressure change only causes a minor change in sea level, the inverse barometer effect. But, under specific conditions, something much more powerful happens: Proudman Resonance. Proudman Resonance is the critical link. It's when an atmospheric pressure wave travels at the same speed as a water wave in the underlying ocean. This is where the magic, or the frightening physics, happens. The atmosphere's energy is efficiently transferred and amplified into the ocean. For the Tonga event, the lamb wave was moving at the right speed to excite deep ocean waves across the globe. This planetary meteotsunami was unprecedented in the modern era. Tide gauges, DART buoys, and coastal sensors from every corner of the world, from the Mediterranean to the Caribbean, the Pacific to the Atlantic, all recorded the same signal. The initial blast created a massive pressure pulse that radiated outward. This wave was so consistent and so little dissipated that it essentially behaved like a planetary ripple. It took about 38 hours for the wave to complete its first full circuit of the Earth. Then, it continued. Due to the perfect, low dissipation nature of the lamb wave and the efficient energy transfer via Proudman resonance, the wave circled the planet a second time, still clearly visible in the data. And then, incredibly, a third time, fading only as its immense energy finally dispersed. The sheer scale is difficult to grasp. This was a single ocean wave, though a minor one in amplitude in many places, that traversed distances of over 75,000 miles over the course of several days. While the wave was global, the actual damage was extremely localized. In the open ocean, the wave was often only a few centimeters high, but that changes when it reaches the coast. When a long-period wave enters shallower water, it undergoes a process called shoaling. The front of the wave slows down, but the back catches up, dramatically increasing its height. This is what caused localized surges up to 1.5 meters in some coastal areas, especially those with narrow harbors or inlets, where the resonance effect was amplified. Furthermore, the Tongan event exposed a critical vulnerability. The atmospheric lamb wave arrived hours before the main classic volcanic tsunami wave, the one generated by the physical displacement of water. In places like Japan, the early arrival of the atmospheric meteotsunami was a total surprise. This event forces a fundamental change in how we think about warning systems. We can no longer rely solely on seismic detection. The potential for a planetary meteotsunami generated by a massive atmospheric event, be it a volcano or theoretically a large asteroid impact, is a new global hazard that must be monitored using air pressure systems alongside traditional ocean sensors. The Tongan event turned the Earth into a giant laboratory. It validated century-old physical theories, like the existence of the Lamb wave and the power of Proudman resonance, on a scale never before witnessed. Today, scientists are rigorously studying the data from that planetary ripple. We learned that the atmospheric pressure waves retained their energy because they were confined to the lower atmosphere, acting as an incredibly efficient conduit to drive the ocean. But what truly astonished scientists wasn't just the global reach of the wave, it was its precision. Around the world, from Alaska to the Azores, every sensor registered the same rhythm. Each crest and trough arrived almost perfectly on schedule, as if the planet itself had been struck like a massive bell. This wasn't chaos, it was coherence, a resonance of air and ocean synchronized on a planetary scale. At NASA and the Japanese Meteorological Agency, researchers traced the data backward, overlaying the pressure waves with satellite infrared imagery. They found that the eruption's shockwave had climbed more than 50 kilometers into the mesosphere, where it ricocheted like an echo through the upper atmosphere before returning to Earth. Each reflection re-energized the surface wave, sustaining its journey. And here's the paradox. This planetary pulse was both violent and delicate. It carried enough energy to alter atmospheric pressure across the globe, yet it was so evenly distributed that airplanes flying above barely felt it. The Earth absorbed the blow like a living organism, dispersing pain through every nerve. For the first time, humanity witnessed the entire planet respond as a single system. Oceans, air, and land trembling in harmony, reminding us that every eruption, every storm, every breath of wind belongs to one continuous, breathing world. The wave that circled the planet 3 times wasn't a destructive giant, but it was a profound scientific event. It confirmed that the ocean and the atmosphere are coupled far more intimately than we realized. The sky can, and sometimes does, move the seas. From a single volcanic eruption in the South Pacific, we gained a new understanding of global energy transfer, redefined the speed of an ocean wave, and uncovered a new, fast-acting hazard. The next time you feel a shift in the air pressure, remember the day the atmosphere made the ocean waves circle the world. If you enjoy understanding the science that shapes our world, subscribe, and let the next mystery find you. Veil Origins: Impossible Truths.